Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 4, Lesson 5. In this lesson, I just have a couple smallish things to teach you, and then I want to do some example problems and give you an opportunity to practice what we've been learning. So if there is a circuit, let's say there's a battery and some resistors. We'll just look at a very simple circuit, one battery and a couple resistors. In real life, I might want to measure what the current is here through this resistor. So listen carefully. We could calculate, do some equations, and calculate based on this voltage and this resistance and this resistance. We could calculate and predict how many amps of current this is going to be. But then in real life, we would also like to measure that. So, I would measure a distance with a ruler. I would measure my weight with a bathroom scale. I would measure some events, durations with my watch or a stopwatch. So I would measure the current with a device called an ammeter. Now, I think it should be called an amp meter, but it's not called an amp meter. It's called an ammeter. But an ammeter measures the current in the unit amps. So what we do with an ammeter, we're just going to draw an ammeter. It's a little box, and it's got two wires coming out of it. So this represents the box, and I'll put a capital A on it, and then it's got two wires coming out of it. The question is, what do I do with the ends of these two wires? And there's a couple different things that you might imagine. You might imagine connecting like this, and then putting the ammeter here, and then connecting this. Or you might say, instead, why don't I, connect right here, and then put the ammeter here. So the green thing and the purple thing are two different ways of connecting a device here. Pardon me. One of them is correct for an ammeter, and one of them is incorrect. And let's think about it. I would call this connection parallel. Current travels junction. Some current goes through here, other current goes through here. I would call that parallel. Again, all the current comes to this junction. Some goes through one, some goes through the other, and then it all comes back. Maybe that's what we're interested in. Or, I need a little sip. Pardon me. Or maybe we want this other way, where all the current goes through the resistor, and then all the current goes through this device. That would be series, all through one, then all through the other, versus parallel, some through one and the rest through the other. And what I'm going to say is the current through here and here don't necessarily have to be the same as each other. So this would not be a good way to connect it. So just mentally erase that. And this is how I connect an ammeter. Because what an ammeter does is it reports the current through itself. This says the current through me is this many amps. Well, since this resistor and this ammeter are in series, the current through here and the current through here are the same. So if this says the current through itself, it's also telling you the current through this resistor. Yay! So the result is that we want to connect an ammeter in series. Very important thing to know. Because if I connected it in parallel, well, it would say how much current's going through itself, but that wouldn't necessarily be the amount of current going through here. Now, the other thing we need to know about an ammeter is, does an ammeter itself have very much resistance? So if I have a circuit here, we gain potential, we lose potential, we might lose potential depending on whether or not it has resistance, and then we lose potential. If the ammeter has resistance, it's going to decrease the current through the whole circuit. The total equivalent resistance before I put the ammeter in is this resistance plus this resistance, which determines the current, I. If the ammeter has resistance, I'm going to press pause here and try to remember what sentence I'm in the middle of. I'm back. Goodness gracious, what was I saying? So I was talking about the current that goes through here. And I was saying that if this has a resistance more than 0, then when I put it in here, it will decrease the current in the circuit. And so then I that I'm measuring will be less than what I was before. And what I want to do is I want to have this device that I can stick in here and tell me what the current is, not what the new current is. I want the current not to change and have it tell me what the current is. So what we say about ammeters is ammeters should have very, very low resistance, because they really can't have no resistance. But we say that the resistance of an ammeter is very close to 0. Resistance is very small. Now, this is important stuff to know about ammeters. You know, how do you build them? You know, they have low resistance. How do you connect them? You connect them in series. What do? They tell you the current through themselves, which by extension, because of the way we hooked it up, also tells you the current through other things in the circuit. These also tend to be great multiple choice questions. The current in an ammeter is, you know, the same as or different from the current in the other devices with which it's in series. The resistance of an ammeter is small. You connect an ammeter in series. Now, why did I draw this other thing? Well, because this is going to be something actually that we call a voltmeter. It's going to tell you the potential difference across itself. It reports the potential difference which is the voltage across itself. So it says, hey, the difference in the voltage here and the voltage here is this many volts. But since I've connected it in parallel with this resistor, the potential difference across it will be the same as the potential difference here. So that's useful. So what do we know about a voltmeter? It should be connected in parallel. Connect it in parallel. Connect an ammeter in series, connect a voltmeter in parallel. They each tell you about what happens through itself. And what do you think about the voltage of this voltmeter? Is it going to be really, really low, practically 0, or really, really high, essentially infinity? Turns out that a voltmeter has very high resistance. Very high resistance. And you might think, oh, that doesn't sound very practical. Turns out it is, though. I want what's going on before to still happen after when I connect the voltmeter. If the voltmeter does not have high resistance, then some current will travel through here, which means that less current will be traveling through here. I don't want to change the current through here. So if I have super high resistance, then essentially no current travels here, and all the current continues to travel the way it was traveling before. So this having very low resistance, this having very high resistance, the purpose thereof is so that the current does not change from before I connect them to after I connect them. This little tickle's driving you crazy, I know. Okay, that is ammeters and voltmeters and how we connect them, what they do, and if they have high or low resistance. Now let's do an example problem. Very fun example problem. So here's a circuit. Let's just look at it. There are two batteries. They both tend to make the current go up over here. And then the current goes up, it goes through a resistor, it comes down through a resistor. Some of the current will continue down through these two resistors. Some of the current will go in here through this resistor. So there we have it. We've labeled the currents I1, I2, and I3, and the purpose of the problem is to find these three currents. Now, yes, these two resistors are in series. You could combine them if you wanted. 2 ohms plus 4 ohms is 6 ohms. These two are in series, so 5 ohms plus 1 ohms is 6 ohms. So that could certainly be done. But the fact that there are two batteries does not allow us to get to that super simple circuit with just one battery and one resistor. So what we're going to need to do here is use Kirchoff's rules: loop rule, junction rule. And this problem is set up with 1, 2, 3 variables. So you might guess that we're going to write 3 equations. We're going to write 2 loop equations, and we're going to write 1 junction equation. You could either write the junction for here or for here. Either way, it'll give you the same information. The question is, which 2 loops are you going to choose? Are you going to choose the top loop and the bottom loop, the top loop and the outer loop, or the outer loop and the bottom loop? So here's what I want you to do. I want you to think about this, press pause and think for a few moments. Don't do the whole problem. Just press pause and either write this junction rule or this one, and select 2 loops, top and bottom, top and outer, left and outer, and write those 2 loop equations. So spend 3 or 4 minutes on that, and then come back and see if you get the same equations as me before you go about solving them. Okay? So 3 equations, work on those right now. And hopefully now you're back. If you haven't pressed pause yet, press pause and do that. But so here's what I'm going to write for my junction equation. I'm going to write I1, which is the current in, equals I2 plus I3, the current's out. I hope that makes sense. Now, for the loops, current's going this way, and then it tells me to go this way. So I'm going to write an equation for the top loop. So let's write that. I'm going to start here, and I'm going to say 24, because I add 24 volts, minus V, the potential difference, equals IR. I, the current through, R, the resistance. So I'm going to write I1 times 2. This current is I1. All of this is I1 times 2 minus I1 times 4. And then I'm making this loop, so I'm going to say minus I3 times 3. Minus I3 times 3. And I get back where I started, so I say equals 0. That is the Kirchoff's loop rule for the top loop. 24 minus I1 times 2 minus I1 times 4 minus I3 times 3, get back where I started, equals 0. So the top loop, or I could have gone this way. See how this current goes down? So I could have done the outer loop. So let's again start here and do 24 minus, and I'm still going to go here and here. So minus I1 times 2 minus I1 times 4. But instead of traveling left, now I'm going to go down and go I2 times 1 minus I2 times 5 plus 12 equals 0. Got it? So now I have 3 equations. I1, I2, I3, I1 and I3, I1 and I2. So I have 3 equations with 3 unknowns. And we can solve them. Now, let me just simplify these two. This says I1 times 2. This says I1 times 4, which is really I1 times 6. 24 minus 6I1. I wrote 6I1 instead of I1 times 6. It just feels more like algebra. Minus 3I3 equals 0. And then I've got 24 plus 12, that's 36, minus I1 times 2, I1 times 4, minus 6I1, minus 5I2 equals 0. So now I have 1, 2, 3 equations that I can solve for 3 unknowns. So it's just algebra. In terms of the physics, we're sort of done. We're almost done. We have to do the algebra and then interpret the answer. That's why I say we're not totally done with the physics. But we need to do this algebra. So what I would suggest now is press pause and spend a few minutes and see if you can do the algebra on your own. And then press unpause and see if you get the answer that I get. Okie dokie. And so press pause and do that. And then, magically, here I am back. I hope you got the right answers. Let's see. This equation has I1 and I3. This equation has I1 and I2. So if I substitute I2 plus I3 for I1, then I'll have 2 equations with I2 and I3. So I'm going to do that. I'm going to write 24 minus 6I1 minus 3I3 equals 0. So I wrote 24 minus 6I1 minus 3I3 equals 0. And instead of I1, I'm going to write I2 plus I3. And I'm going to do the same thing here. 36 minus 6I1 minus 5I2 equals 0. And instead of I1, I'm going to write I2 plus I3. I did this substitution. See it? All right. So now I have 2 equations and 2 unknowns. 24 minus 6I2 minus 6I3, 7, 8, 9, minus 9I3 equals 0. So here's the 6I2. Minus 6I3 minus 3I3 is minus 9I3. 36 minus 6I2 minus 5I2 is minus 11I2 minus 6I3 equals 0. All right. So now, 6 times 1.5 is 9. Negative 6 times negative 1.5 is positive 9. So I'm going to multiply all these 3 by negative 1.5. So I'll get a positive 9, and then I can add these 2. So negative 1.5 times 36 is negative 54. Negative 54. 36, a half of 36 is 18, 36 and 18, 36, 46, 54, negative 54, good. When I multiply negative times negative, I get positive. 11 times 1.5 is 16.5. 16.5 I2. Half of 11 is 5.5. 5.5 plus 11 is 16.5. And then 6 times 1.5 is 9. Plus 9I3 equals 0. So then I cross that out. And then I'm going to add these 2 equations. And the reason is negative 9 plus 9 is 0. Yay. 16.5 minus 6 is 10.5 I2, and 24 minus 54 is negative 30 equals 0. I'm just going to shut up for a second and do the math without talking at the same time. Okay, I think I did it right. Move the 30 to the right and it becomes positive 10.5 I2 equals 30. Divide both sides by 10.5 and I get I2 equals 30 divided by 10.5. 2.86. 2.86 amps. And this is I2, which is not quite what the book got. Well, it's sort of close to what the book got, but not quite what the book got, which annoys me. Feel free to tell me if you see I made an algebra error in there somewhere. Then once we know I2, we simply plug it in here and you can find I3. And once I know I2 and I3, I add them together and I get I1. So let's see, I2, let's go here. 36 minus 6 I1 minus 5 times 2.86 I2 equals 0. I'm going to move I1 to the right. I1 equals all that stuff over 6, which is 36 minus 5 times 2.86. So 2.86 times 5, make it negative, add it to 36, divide by 6, and get 3.53 equals 3.53 amps, which is pretty close to what the book got. I wrote down the book's answers. So there's I1, there's I2, and when I add those, I1 plus I2 equals I3. I3 equals 3, 4, 5, 6.3, about 6.4 amps, which is not. What am I looking for? Oh, wait a minute. What am I looking for? Here's I1, here's I2. I1 is not I1 is I2 plus I3. So I3 is I1 minus I2. I1 minus I2. I1 3.53, 2.86, 0.67. Let's give it a try. And oh my gosh, if I get into roughly one more time, I'm going to straighten. There we go. Tell me if you get a different answer. If you see I made an algebra error, that would be so fun to hear from you. All right, final problem. Example problem. Let's look here. Again, we have a beautiful circuit, and it asks us to find a potential difference between these 2 points, A and B. I've got 3 batteries. They're all trying to make the current go this way, except we really can't have any current go this way. This is what's called an open circuit. No current flows here. Oh, so if no current flows through here, I know this potential difference is just going to be 0. This current here is 0 amps. Okay, well, this is 12 volts and this is 8 volts. 12 is more. So the only current that happens in this whole problem is this current right here. And it goes counterclockwise because 12 is more than 8. So we gain 12 volts, we lose 8 volts, we lose. Interesting. We have kind of a simple circuit here. Let's start right here and draw a loop rule. There is no junction rule, even though this looks like a junction and this looks like a junction. There's no current through here because this is an open circuit. So all I have is 12 minus 10I. V equals IR, so I could write, I1 times 10, but there's only one current, so I'm just going to call it I instead of I1. And instead of I times 10, I'm going to write 10I1. Same thing. Minus 5I minus 8 volts, because I'm going the wrong way. Minus 2I minus 3I equals 0. Well, that's not so hard. 12 minus 8 is 4. 10, 15, 16, 17, 18, 19, 20. Minus 20I equals 0. So move this to the right and it becomes positive 20. Divide both sides by 20. 4 over 20 is 1/5, or 0.2. I equals 0.2 amps. So this current is 0.2 amps. Interesting. That's not what we asked to find. We're asked to find this potential difference. So what's going on here? Let's say the potential here is 0 volts. Then the potential here is going to be 12 volts, because I added 12. And then I'm going to lose 10 times 0.2, which is 2 amps. So 2 volts. So 12 minus 2, the potential here is 10 volts. I'm going to lose 1 volt. 5 times 1/5 is 1. So if I lose 1 volt, this is the potential of 9 volts minus 8 volts, right, is 1 volt minus 2 times 1/5 is 2/5. 1 volt minus 2/5, or 1 volt minus 0.4 is 0.6 volts. Minus 3 times 1/5 minus 3/5, and 3/5 is 0.6. So 0.6 minus 0.6 gets me back to 0. So there we go. The voltage here is 0. The voltage here is 12. The voltage here is 10. The voltage here is 9. The voltage here is 1. The voltage here is 0.6. The voltage here is 0. I gain potential. I lose. I lose. I lose. I lose. I lose. I lose. Now the potential difference between here and here is 10 volts. The potential difference across here, V equals IR, I is 0. So there's no potential difference. So this is still 0.6 volts. So the potential difference across here, it's a battery. So I'm going to gain 4 volts. So it's 4.6 volts here. What's the potential difference between 4.6 and 10? 5.4. So the delta V here equals 5.4 volts. And that is the answer the book got. So we got the same answer as the book here. All right. Well, I hope you had a good time. I hope it all makes sense. If not, write down the timestamp, write down a question, and you know how happy I am to talk about these things in class. Have a wonderful weekend. But whatever you do, don't break the laws of physics.